How do we graph an exponential function? Well, an exponential function takes the form, in general, of y equals a to the exponent x, where a can just be any number, right? And the most common one we see usually is y equals 2 to the exponent x. So with this example, we can go ahead and we can make a table of values, and we can try to figure out what's happening here, right? Let's say you have -3, -2, -1, 0, 1, 2, 3, just like that. And you plug these all in to your function. If you plug in -3, well, 2 to the -3 is equal to 1 over 2 to the 3, which is 1/8. So you're going to get an eighth here. If you plug in -2, you'll get 1 over 2 squared, which is 4, so you get 1 over 4. If you plug in -1, you get a half. If you plug in 0, well, anything to the exponent 0 is just 1. If you plug in 1, you get 2. If you plug in 2, you get 2 to the 2, which is 4. If you plug in 3, you get 2 cubed, which is 8. So you can see from this pattern that every time you go to the next number, what's happening? Well, you're multiplying by 2, right? Each number is 2 times as big as the last number. That's actually part of the proof as to why 2 to the exponent 0 is equal to 1, because that allows it to fit into this pattern. Now, with that in mind, we can go ahead and we can graph what this might look like, right? Just as a sketch. So here's your x and y axes. So let's plot these points. So at 0, you're at a height of 1. Put that there. At 1, you're at a height of 2. At 2, you're at a height of 4. And at 3, you're at a height of 8. So each point is twice as high as the last point, right? At -1, you're at a height of a half. At -2, you're at a quarter. At -3, you're at an eighth. So it gets harder and harder to show how close these dots are to the x-axis, right? And actually, the smaller the number is, when I say smaller, I mean farther to the left, right? The bigger negative the number is, right? The bigger negative numbers, like -10, -20, -100. As you go very far to the left, you're going to get very, very close to this x-axis, but you're never going to touch it, right? There's no number small enough, right? Like -1,000,000, for example. Even if you plug in -1,000,000 here, this is never going to become 0. It's just going to get smaller and smaller and smaller. And one way to think about that is by saying that there's a horizontal asymptote here on your x-axis. And I can show that with a dotted line, right? So you have a horizontal asymptote right here at y equals 0. Horizontal asymptote at y equals 0. Right? The x-axis has an equation of y equals 0. Right? It's a straight line going through the y value of 0. So that's your horizontal asymptote. And now you can connect these dots, right, all together, and you get this nice exponential curve if you draw it, appropriately like that and like this. So down here on the left, you're getting closer and closer and closer to the x-axis, but you never touch it. And then here you're going up and to the right forever, but it's getting, but it's increasing ever quickly, right? Every point, it's going up twice as fast, right? Twice as much. If you look at the height at 1, it's 2. The height at 2 is 4. The height at 3 is 8. Each time you go over 1, the height doubles. So it's increasing exponentially. That's why it's an exponential function. Now, we can look at some different graphs that follow the same idea, like y equals 2 to the x plus 1. So this is the same as the last function, except now there's a plus 1 here. And if we wanted to sketch this, that plus 1 really just moves your whole graph up 1 unit. And so your horizontal asymptote, instead of being at 0, will be up here at 1. So you'd say you have a horizontal asymptote at y equals 1. And then you'd go ahead and you would draw the curve just like this. And the y-intercept you could find, right, before the y-intercept was 1, now it's moved up 1, so it's at 2, right? You could figure that out also by just subbing in 0 for x. 2 to the 0 is 1, 1 plus 1 is 2. So your y-intercept is there at 2. You can do another one. You could say y equals 2 to the x minus 2, and it's the exact same idea. You go down to -2. That's where your horizontal asymptote is. So you say horizontal asymptote at y equals -2. You draw your line like that. The y-intercept, plug in 0 for 2, or plug in 0 for x. 2 to the 0 is equal to 1. 1 minus 2 is -1. So you have a y-intercept at -1. And you could also figure out the x-intercept, right? In the past, we didn't have an x-intercept because it was above the x-axis. But now, of course, you can see you will have an x-intercept. So to find the x-intercept, you set y to 0 and solve for x, right? So if y is 0, 0 equals 2x minus 2. Move 2 to the other side. 2 equals 2 to the x. Well, this 2 is to the exponent 1. So if 2 to the 1 equals 2 to the x, then 1 must equal x. So this here must be a value of 1. So your x-intercept is 1. Okay, let's look at another example. Let's say you have y equals 2 to the exponent x plus 1. Okay? What's going to happen here? Well, your asymptote isn't moving up or down because there's no number on the end of your function being added or subtracted. Instead, the number being added is in the exponent with your x. When you think back to our work with transformations, that should tell you that we're shifting the function to the left 1 unit, right? But when we're graphing this and we want to graph it accurately, the thing to pay attention to is your intercepts, right? So we should figure out what the new y-intercept is. So set x to 0, right? If x is 0, you get 2 to the 0 plus 1, which is 2 to the 1, which is 2. So you now have a y-intercept of 2. So when you draw this, it's going to look like that. And that makes sense because it used to cross here at 1, but the point that was there has now moved to the left 1 unit. It's now over here at -1. So you also have this point, -1, 1. And you can confirm that by plugging in -1 for x. -1 plus 1 is 0, 2 to the 0 is 1. So that point is in fact located on your curve. It used to be here, but it's moved to the left 1. Let's do another example. Let's say you have y equals 2 to the x minus 1. Well, we can probably guess what's happening here. The graph is moving to the right 1 unit. And so if we move to the right one, still the basic shape, right? But now this point that used to be here at a height of 1, it's moved to the right 1. So now that point that has a height of 1 has moved to the right, and it has an x value of 1. And you could figure out the y-intercept again, right? Just set x to 0, and you would get 2 to the 0 minus 1, which is 2 to the -1, which is 1/2. So this here is a half, right? That's a y value of 1/2 right there. Okay, let's look at another example. What if you have y equals -2 to the exponent x? Well, that negative on the front, that indicates a vertical reflection, right? We're flipping the whole thing down. And if you think about it from the perspective of a table of values, every number you used to get here is now being multiplied by a negative. So all the y values are negative, meaning when you graph this, it's going to look like this, where this y-intercept is now -1 instead of +1. And you can confirm that by plugging in 0 for x. 2 to the 0 is 1, and you have -1. So this is what that would look like. Let's do another one. Let's say you have y equals 2 to the -x. So this one's interesting, right? Because now the negative is in the exponent with the x. And if you recall from our transformation work, that would typically indicate a horizontal reflection, or flipping sideways. And in fact, that's exactly what's going to happen. And if you want to make a table of values to see how that works, plug in the x values again, -2, -1, 0, 1, 2. Plug those in for x. If you plug in -2, 2 to the -2, that just becomes 2 to the 2, which is 4. So you get 4 here. Remember, you used to get 1/4, now you're getting 4. Plug in -1, you get 2. Plug in 0, you get 1. Plug in 1, you get a half because it's no longer 1 in the exponent, it's -1. Plug in 2, you get a quarter. So these y values used to be up here, and these y values used to be here. They've all flipped, meaning that horizontally, our graph is going to flip as well. If you plot these points, you get a graph that looks something like this. And it has the same y-intercept, right? That's still at 1. But your graph just flipped horizontally, because remember, it used to look something like this, and now it's just the mirror image of that. And what's interesting is that that function is actually the exact same function as 1/2 to the exponent x. Because if you think about 2 to the -x, you can split that up to be 2 to the -1 to the x. If you recall your exponent rules, these just multiply together to be this. And that's equal to a half times x. So this function and this function are actually the same thing. So if you ever have an exponential function where your base is a fraction, like 1 over 2, that just indicates that your graph is sort of a horizontal reflection to what we're used to, right? It's going down instead of going up. Or in other words, what we have is exponential decay versus exponential growth, right? This general shape is what we would call exponential decay. And if you have a shape that is going up like this, that's what we would call exponential growth, right? Because it's growing, this is decaying, it's going down. Now with that in mind, we'll do a couple examples here. Let's say we have y equals negative 4 times 2 to the exponent 2x minus 1 plus 3. So let's try to graph this. Now, unlike when we try to graph other types of functions where we start with the parent function and then make our changes, for exponential functions, it's sometimes useful to just figure out some key components and then connect the dots. And what I mean by that is find your y-intercept, find your x-intercept, figure out where your asymptote should be, and then connect the dots and make your curve. That's usually the most accurate way to draw these. So let's start with the y-intercept. To find the y-intercept, you set x to 0. So y equals negative 4 times 2 to the exponent 2, 0 minus 1 plus 3. Well, 0 minus 1 is negative 1. Negative 1 times 2 is negative 2. Okay, so we have negative 4 times 2 to the negative 2 plus 3. What's 2 to the negative 2? Well, 2 squared is 4. The negative makes it flip, it becomes 1 over 4. So you get negative 4 times a quarter plus 3. Negative 4 times a quarter, that becomes negative 1. So you get negative 1 plus 3, and that equals 2. So your y-intercept for this is going to be 2. So just label that right there. Okay, now let's find the x-intercepts. How do you find the x-intercepts? Well, you set y to 0. So 0 equals negative 4 times 2 to the 2x minus 1 plus 3. I'm going to move the 3 to the other side and then divide both sides by negative 4. So you get negative 3 over negative 4. Those negatives are going to cancel, so you could actually just write 3 over 4 on the left side. So 3 over 4 is equal to 2 to the 2x minus 1, like that. So on the right here, we can split up that exponent to be 2 squared to the exponent x minus 1, or in other words, 4 to the exponent x minus 1, just like that. And then we can actually do something kind of interesting here with our 4 to the x minus 1, because if you recall exponent rules, if you have something to the exponent of something minus something, that's the same as saying this, right? 4 to the x divided by 4 to the 1 is equal to 4 to the x minus 1. So typically we go this way, right? We change this to this, but we can also go the other way, right? Again, that's from your exponent rules, so review that video if you need to. So that's equal to 3 over 4. So multiply both sides by 4, those 4's go away, and we're left with 3 equals 4 to the x. Okay, so what's x equal to? Well, if x was 1, then this whole thing would be equal to 4, right? So let me actually write that out. If you had 4 to the 1, that would give you 4. If you had 4, let's say like to the 1/2, what would that equal? Well, that would equal 2, because remember, raising something to the exponent of a half is the same as taking the square root of it, right? So that would be equal to 2. So the answer for x has to be between a half and 1, right? So you could say x has to be in between a half and 1, because when it's a half, you get 2. When it's 1, you get 4. 3 is in between those answers. So your real x value is somewhere between 1/2 and 1. And for now, you can do a little bit of trial and error, and you can figure out that x is equal to approximately 0.8. Right? That's a little bit between 1/2 and 1. Now, it's not that important that you're that accurate with this. We just needed it for the sketch, right? So our x-intercept up here in the sketch is going to be 0.8. So right about there. Again, that's approximate. There is a way to find that answer precisely to a more precise decimal. And we're going to be covering that later in these videos. But for now, your teacher might just expect you to use trial and error to get a rough estimate. Now we're going to connect these dots together, and you can probably see the general shape as to what this is going to be. You know, something like that, right? Because there's a dot here, that's really the only way to connect them. Although you could do something like that, I suppose. So it's a little unclear, right? But this is the way that jumps out to me. And the reason I say that, if you notice the original equation up here, you have a negative on the front, telling us that this function's been reflected vertically. So in the past, when a function looks like this, it flips down to look like this. That's a vertical reflection. So in this case, I think this is the general shape, and you probably have a horizontal asymptote, right there, right? And you get closer and closer to it as you go to the left. Question is, where's that horizontal asymptote? Well, because I have this +3 on the end, it should be clear that your horizontal asymptote is at +3, right? You can label that at 3. Right? You could even label it as horizontal asymptote at y equals 3. Right? And if you want to check your answer, you can plug in a value for x that's very far to the left, and when you calculate it, your y value should be almost at 3, right? It should be approaching it. So if you plug in like -100 for x, this is going to be very, very, very small. You can multiply that by -4, you'll get a very, very, very tiny number that's negative. And then when you add that to 3, you get a number that's just under 3. So hopefully you can visualize why, algebraically, you get a horizontal asymptote at 3. Okay? But if you forget, just look for this number on the end of your exponential function. All right? And that's that question. Let's do another one. Let's say I have f of x is equal to a times b to the exponent x. What do we know about these numbers? We know what b is, right? B is your common ratio. What does that mean? Why am I saying that b is the common ratio? Well, because if you recall, when we did the table of values, I said that each number goes up 2 times, right? From one to the next. You double each number to get to the next one. That number 2 came from the base, right? Your b value. The b value represents your common ratio. And you have your a number here, the number on the front. And what does that represent? That represents your initial y value. In other words, the y value when x is equal to 0. In other words, it's your y-intercept. So typically, if you just had, y equals 2 to the x, your a value would just be a 1. It's kind of hidden. And that's why you have a y-intercept of 1. So with this in mind, we can actually graph things a little bit more simply, right? So let's say you have f of x equals 2 times 2 to the x. So 2 is the y-intercept, so you put a 2 there. And the common ratio is 2, meaning that when you go over 1, you're going to double your height, so you'll be up here at 4. If you go 1 to the left, your height will go down by a half, so it's going to be here at 1, right? And then you just continue that pattern. You can actually plot some more points if you want to. Likewise, if you're given this graph here, and you're asked to find the equation, you can do that, because you know what the y-intercept is from looking at it, and you can figure out the common ratio by looking at one point and then the next point. So let's say you want to do that, right? Let's say you're given a function, the graph itself. So you're given this graph here, goes something like this, and you're told some points, right? You're told this is 2. You're given this point over here, this is -1, 4. And then up here at a height of 8, you have -2. Could I figure out what the equation that represents this function looks like? Yeah, I think so, because if you made a little table of values here, and you had -2, -1, 0, and then 8, 4, 2, you could see that from going from here to here, you're multiplying by a half, right? So the common ratio is a half. That's your b value. Now you know the starting point is 2, right? The y-intercept, you get that just from looking right here, or right here. That's a. So if you want to figure out what this equation is, you could call it g of x if you want, something like that. G of x is equal to a, which is 2, times b, which is a half, to the exponent x. So this is an equation that represents this function. Now you also could have written this as g of x equals 2 times 2 to the negative x, because as we talked about before, 1/2 is the same as 2 to the -1. So this would also work, but this is really where you should start, right? Find your b value, find your a, and then plug it all in together, just like that. Let's do one more. Let's say you're given a table of values, x and y, and you have these points, -3, 1.5, and 4, 3,280.5. Kind of random, right? But you're asked to find the equation of this function. And so you say, all right, g of x equals a times b to the x. That's our general form. How do we find what a and b might be equal to? Well, first off, we can plug in a point, right? We can plug in this point to start if we want. You could say 3280.5 is equal to a times b to the exponent 4, because x in this case is 4. And this next step is pretty interesting, but what you're going to do is you're going to divide that by the equation when you plug in the other point, because this is going to allow you to find the common ratio, right? So you plug in 1.5 equals a times b to the exponent -3. So 3280.5 divided by 1.5, you're going to get 2187. A divided by a, those cancel. B to the 4 divided by b to the -3 is b to the 7, because 4 minus -3, that's like 4 plus 3, which is 7. So now to solve for b, take the 7th root of both sides. So the 7th root of 2187 is equal to b, which is equal to 3. So b is equal to 3. Now that's b. How do I find a? Well, we can set up our equation and we can plug in a point, right? Let's plug in -3, 1.5. So 1.5 is equal to a times b, which is 3, to the exponent of x, which in this case is -3. And now we can solve for a. So divide both sides by 3 to the -3. A is equal to 1.5. When you divide by 3 to the -3, that's really like multiplying 3 to the 3. So just to keep it simple, we could do that. And then when you multiply these together, 3 to the 3 is 27 times 1.5 is 40.5. So a equals 40.5. And so between those two pieces of information, our a and our b, we could say that g of x must equal 40.5 times 3 to the exponent x. This is the equation that represents that function.